Again, Kuya Joshua Pinosada, and this is my video discussion about how CPU works, the evolution of CPU, part 1 to part 4, the overview of the GPU, the SOC 1 operations, and the SOC 1 programming. So let's start from how the CPU works. So the Central Processing Unit, or the CPU, is often called the brain of the computer. It is responsible for executing instructions, processing data, and controlling all operations inside a computer system. Every time you open an application, type on a keyboard, or browse the internet, the CPU is actively working behind the scene. So, to understand how a CPU works, we need to learn its main components and the process it follows to execute instructions. So, the first one, for the main components of the CPU, the control unit. The control unit directs all activities of the CPU. It tells other components what to do and when to do it. So the function it fetches instructions from memory, it decodes instructions, controls data flow between CPU, memory, and the input-output devices. So for example, if you press a keyboard or a key on the keyboard, the control unit tells the CPU to read the input, process it, and display it on the screen. So number two is the arithmetic logic unit, or the ALU. So the ALU calculations and logical operations. So the functions, for example, for the arithmetic operations is the addition, subtraction, multiplication, and division. So for the logical operation, it is and or not or comparisons. So for example, we have 5 plus 3, it is equals to 8. That is a example of arithmetic operation. Then is 10 is greater than 7. So it is a logical comparison because we have the greater than. Then number 3 is the registers. So registers are very small, very fast memory locations inside the CPU. They temporarily store data and instructions currently being used. So for example, for the registers is the program counter or the PC. It holds the address of the next instruction. Then the instruction register, or the IR, it holds the current instruction. Then lastly, we have the accumulator, which it stores in intermediate results. So for example, when we calculate 4 plus 6, the numbers in the result are stored temporarily in registers. So the CPU instruction cycle. The CPU follows a continuous process called the fetch, decode, execute cycle. So we're now in the instruction cycle in for the CPU. So what is the processes? And that is the fetch, decode, execute cycle. So step one, we have the fetch. So the CPU fetches the instruction from the main memory, or the RAM. So for example, we have the instruction add 4 comma 6. So the control unit fetches this instruction using the program counter. Then step 2, decode. The control unit decodes the instruction to understand what action is needed. So for example, the CPU, it understands that it must add the two numbers 4 and 6. Then for the step 3, we execute. The ALU executes the instruction. So for example, the ALU, it adds 4 plus 6, it is equal to 10. And it stores the result in a register or memory. So the step 4, which is store, which is the result is stored in a memory if needed. So for example, the value 10 is saved so it can be used later. So for simple real life analogy, think of the CPU as as a chef in a kitchen. So the recipe going to instruction, to ingredients, to data, to the chef. So the chef or the CPU processes those ingredients. and the dish is the output. The chef follows steps just like the CPU follows the instruction cycle. So in summary, the CPU works by fetching instructions, decoding them, executing them using the ALU, storing results. So through the coordination of the control unit, ALU, and registers, the CPU enables computers to perform tasks quickly and efficiently. The evolution of CPU processing power, Part 1. The mechanics of a CPU. So for the introduction, the birth of a revolution. In the mid-1960s, a revolution in miniaturization began that would change the world forever. It started with the idea of packing transistors onto a single silicon chip, creating the integrated circuit. Then, the landmark moment came in March 1971 with the Intel 4004, the first commercial central processing unit, or the CPU. So, originally built for a Japanese calculator, this time chip contained 2,300 transistors and could execute up to 92,500 instructions per second. So that was fast. So to put that in perspective, the ENIAC, one of the first electronic computers, was built only 25 years earlier, weighed 27 tons, and cost the equivalent of $5.5 million today. Yet, it could handle only 5,000 instructions per second. So, what is an instruction? But what exactly does a CPU do every time you use a computer, whether you're playing a game or just typing 22 divided by 7 into a calculator, you are issuing an instruction. So, at its core, a CPU is an instruction processing machine. These instructions are represented by bits, the binary zeros and ones that indicates on or off states. So when we group 8 bits together, we get a byte, which can represent 256 different states. So modern CPUs use words to process data, while the original Intel 4004 was a 4-bit processor, meaning it moved data in a 4-bit chunks. Today, 64-bit processors can represent over 18 quintillion discrete states, allowing for massive calculations and high-speed performance. So also, we have the fetch, decode, execute cycle. So to process these instructions, every CPU follows a three-step loop: fetch, decode, and execute. So fetch, for the fetch, the CPU retrieves an instruction from the random access memory. It uses a highway called a bus to communicate. The address bus tells the RAM which specific location to look at, and the data bus carries the information back to the CPU. Then once the CPU has the data, it breaks it down into two parts, the opcode and the operand. The opcode is the command, like add or remove, and the operand is the data being acted upon, like the number 5. So next is execute. This is where the work happens. CPU's arithmetic logic unit takes the operands and performs the math or logic required. The result is then stored in a register, a high-speed internal notepad, or sent back to RAM. So we have then the logic and branching. So CPU isn't just a calculator, it's a decision maker. It does this through branching. So unconditional branching is a simple jump to a new part of a program. Conditional branching allows the computer to make decisions. For example, if the result is 0, jump to this instruction. If not, keep going. This ability to test conditions and change course is what allows software to have logic and react to user input. All of this happens within internal registers, like the program counter, which keeps track of exactly which instruction is to be fetched next. So, number 5, the clock and performance. What ties this whole machine together, which is the clock. So the clock is a repeating pulse that synchronizes every internal movement. Its speed is measured in hertz. The Intel Core 004 run at 740 kHz or 740,000 pulses per second. Then for today's high-end CPUs like the Intel Core i9, which reach speeds of say 5 gigabyte hertz, that's 5 billion pulses every single second. However, speed comes at a cost. Increasing the clock rates generates immense heat and requires more power. Constant battle for engineers trying to push the limits of physics. So in conclusion for this part, from a 2000 transistor chip in a calculator to the multi-billion transistor powerhouses in our pockets a day, the evolution of the CPU is a story of how incredible engineering is. Understanding these basic mechanics, the bits, the buses, and the fetch execute cycle is the first step in understanding the digital world we live in. Next, we have the evolution of CPU processing power, part 2, the rise of the times 86. So, the 8-bit revolution, as the 1970s progress, the world of computing was on the brink of a massive shift. Intel's early 4-bit processors were giving way to the 8008, an 8-bit successor that introduced larger address capacities and more elaborate instruction sets. Beyond its technical specs, this chip helped launch a small traffic data company called TrackOdata. The two young entrepreneurs behind it is Bill Gates and Paul Allen. While TrackOdata was only a moderate success, it paved the way for their next venture, the Microsoft. So next is we have the indirect addressing and vector tables as one of the most powerful features introduced in this era, which is an indirect addressing. So in the basic, direct addressing, an instruction tells the CPU exactly where the data is. But in indirect addressing, the instruction points to a memory location that contains another address. So think of this like a vector table. If a program needs to choose one of five random sentences, it picks a number between 1 and 5. The program then looks at the table, the vector table, find a specific memory address of that sentence. This allowed for more flexible and dynamic software designs. So next is the hardware interrupts. So the multitasking scene next came interrupts. This mechanism allows hardware like a keyboard or a mouse to interrupt the CPU's current task to handle a high priority event. For example, when you move a mouse, the hardware signals the CPU to pause. The CPU jumps to a specific interrupt service code, updates your cursor position, and then returns to the original program. This ability to pause and switch tasks is the fundamental basis for modern multitasking. So next is the 8080 and the Z80 thread in 1974, which the Intel released the 8080, the first truly usable microprocessor. It could address 64 kilobytes of memory and operate at 3.1 millihertz. However, competition was fierce. Former Intel engineer Federico Fagin designed the Zilog Z80, which became a dominant force in early desktop computing. Then Intel needed a rapid response, leading to a project that would change the history. So this is now the birth of the X86. The Intel 8086 launched on June 8, 1978. The 8086 became the progenitor of the 8 times 86 architecture. It was a fully 16-bit CPU capable of addressing a massive 1 megabyte of memory using a system called segmented memory. This involved using 16-bit windows to look at different parts of the system, RAM, while some programmers found it cumbersome. It allowed the chip to handle significantly larger and more complex software than its predecessors. The next is the stack, and the subroutines, the 86 also refine the stack. The memory mechanism for managing subroutines, the reusable blocks of code. The stack works like a spring-loaded cafeteria tray dispenser. Last in, first out, or the LIFO. When the program jumps to a subroutine, it pushes the return address onto the stack. Once the task is done, it pops That's the address of to find its way back home. If a bug causes the program to push too much or pop the wrong data, you get a stack overflow, causing the machine to crash. Then the CIS architecture and the memory bottleneck, the 8086 solidified Intel's commitment to CISC, or the complex instruction set computing, at a time when memory cost over $50,000 per megabyte. CISC was a brilliant solution. Unlike RISC or the reduced instruction set computing, which uses simple fast instruction, CISC uses complex instructions that do more work per line of code. This means programs took up less space and required fewer load strips to the system memory. Then the floating point math and the IBM PC, finally the Intel introduced the 8087 coprocessor to handle complex decimal math. The floating point operations that the main CPU struggled with. Its power could die of IBM. 1981, the IBM PC debuted with a variant of the 8086 called the 8088. Its runaway process, combined with Microsoft's DOS, turned the 8 times 86 architecture into the global standard for personal computing that remains dominant to this day. The evolution of CPU processing power, Part 3. The origin of modern operating systems. So, the birth of modern operating systems. The era of manual operation and the inefficiency of open shops in the early 1950s. The concept of an operating system as we know it didn't exist. Computers like the IBM 701 were operated in an open shop environment, meaning users physically entered the computer room to run their programs manually. This was incredibly inefficient. For instance, a user might spend 10 minutes setting up punch cards and magnetic plates only to perform 5 minutes of actual computation. Given that the IBM 701 701 cost thousands of dollars per hour to operate. This wasted time represented a massive financial loss, estimated at roughly $146,000 per month in 1954 dollars. This inefficiency necessitated a shift toward closed shops, for professional operators handled the machines and users simply submitted their jobs to the process in sequence. Then the batch processing and the rise of multiprogramming. The first major leap in efficiency came with the invention of batch processing, when the computer began to schedule its own workload through early monitor software. However, significant bottleneck remained the CPU was vastly faster than the mechanical card readers and printers of that time. While waiting for data to be read from a tape or printed, the CPU sat idle. So these developers introduced multiprogramming. Instead of running one job to completion, the computer would keep several programs in memory at once. When the program stopped to wait for hardware input and output, I/O, the CPU would immediately jump to another task. This ensured the processor remained busy as much as possible. Through it, it still lacked the fluid, simultaneous feel of modern multitasking. Then the evolution of multitasking from cooperative to preemptive by the late 1960s. Systems like the DSC TDP6 and IBM's OS/360 MFT began implementing for multitasking. Early version relied on cooperative multitasking, where a program was given control of the CPU and was expected to voluntarily yield control back to the operating system once it's finished a small task. A classic example of the failure of the system is when a single program freezes or enters an infinite loop. In a cooperative environment, the entire computer would lock up because the rogue program never handled back the system to the CPU. This was eventually solved by preemptive multitasking. This model, the operating system uses a hardware timer forcibly interrupt a running process at a specific time slice, ensuring no single application can hog the CPU or crash the entire system. So, for protecting the system, the Memory Management Unit or the MMU, as computers began running multiple programs simultaneously, a new danger emerged. One program would accidentally or maliciously overwrite the memory, of another program, or even the OS or the operating system itself. This led to the development of the Memory Management Unit or the MMU. The MMU acts as a hardware gatekeeper between the CPU and the RAM. It creates a virtual memory space for each program, making the software believe it has the entire memory to itself. If a process attempts to reach outside its sandbox and access memory doesn't own, the MMU triggers a hardware fault, and the operating system immediately shuts down the pending program because it can cause further damage. So, for the security to privilege rings and the legacy of Unix or of Unix, a final piece of the modern OS puzzle was the implementation of protection rings or memory access privileging. Operating systems like Multics, which heavily influenced Unix, introduced the idea of different privilege levels for code. The core of the operating system, the kernel, runs in a ring 0 with full access to hardware. First, user applications run in ring 3 with restricted access. This means an app cannot directly talk to the hard drive or change system settings. It must ask the kernel for permission. This fundamental concept preemptive multitasking, MMU protection, and privilege rings were perfected in the 1970s and remain the bedrock of every Windows, Mac OS, and Linux system we use today. So the evolution of CPU processing power part 4, the 32-bit processor, pipelines, and caches. So the shift to 32-bit computing, the mid-1980s marked a pivotal era where software complexity began to outpace hardware capabilities. Early productivity tools like the core version of Microsoft Word for the OS were incredibly lean, occupying only 150 kilobytes of space. However, as programs transitioned toward feature-rich graphical interfaces, the demand for more memory and processing power skyrocketed. This necessity drove the mainstream adoption of 32-bit architecture. While mainframe computers had 32-bit systems for decades, the consumer market saw its first breakthrough with processors like the Motorola 68020 and the Intel 80386. The Motorola 68020, for instance, was a true 32-bit successor that powered iconic machines such as the Apple Macintosh 2 and the Commodore Amiga 1200. These chips utilized denser packaging to handle the increased signal count required for their expanded architecture. Then the impact of the Intel 80386, it was released in 1986, became a landmark in computing history by redefining the Type-26 architecture. It introduced a sophisticated memory management unit, MMU, that allowed for a flat memory model, enabling memory operating systems to manage up to 4.2 gigabytes of memory. This was a massive leap from previous generations, allowing programs to be loaded into memory fragments without worrying about their physical location, a concept that remains the foundation of modern operating systems, like Windows and Linux. A key example of its influence was seen Compaq used the RAID6 to update the PC-compatible standard independently of IBM, cementing the RAID6 as a dominant force in the desktop market. Furthermore, the RAID6 maintains strict backward compatibility, allowing it to run software designed for the original 8086. Then the boosting efficiency with instruction pipelining. As clock speed increased, engineers face a bottleneck. The traditional fetch decode execute cycle left parts of the CPU idle during different phases. To solve this, they implemented instruction pipelining, which breaks instructions into sequential stages so they can be processed in parallel. Think of it like an assembly line. While one instruction is being executed, the next is being decoded, and the one after that is being fetched. This significantly increases throughput and allows the CPU to run at higher frequencies. However, this method introduces hazards such as when a program branches unexpectedly. This control hazard occurs when a conditional branch path is chosen, and if the prediction is wrong, then the pipeline must be flushed and reloaded, causing a performance penalty. And managing pipeline hazard and prediction to minimize the impact of this hazard, modern processors use advanced techniques like branch prediction, This involves the CPU attempting to guess which path a program will take based on the statistical algorithm. Another technique is pipeline bubbling, where the system inserts empty stages or bubbles to create a delay allowing the data dependency to resolve before the next instruction proceeds. For even higher performance, some CPUs utilize superscalar pipelining, which involves running multiple pipelines in parallel. In this scenario, the CPU processes several instruction paths simultaneously and simply abandons the ones that turn out to be incorrect. This innovation was first seen in early forms within the Motorola 6H220 and the Intel 386, though they were much more limited than the sophisticated versions we use today. Bridging the memory gap with batching. Perhaps the most significant challenging of the 1980s was the widening gap between CPU speed and memory access time. While processors were becoming incredibly fast, standard RAM remains relatively slow. To bridge this gap, engineers introduced caching, a small amount of high-speed static memory that acts as a buffer for a slower main memory. Caching works on the principle of spatial locality, assuming that if a CPU needs one piece of data, it will need the data stored near it very soon. Then, the cache organization performance, the effectiveness of cache is measured by its hit rate, the frequency which the CPU finds the data it needs in the fast cache rather than having to wait for a slow system or RAM. When the data isn't there, it's called a cache miss, which can stall the CPU for hundreds of clocks. To manage this, cache uses different mapping scheme, direct mapping, which is the simplest, where each region of memory has one specific spot in the cache. The more balanced approach is a set associative code caching, which divides the cache into groups, allowing data to be stored in several possible blocks to reduce conflicts. Additionally, replacement policies like least recently used or LRU help the controller decide which data to overwrite when the cache is full, ensuring the most relevant information stays accessible. So for the overview of the GPU, or the graphics processing unit, it is a specialized electronic circuit designed to manipulate and alter memory to accelerate the creation of images in a frame buffer intended for output in a display. Unlike a CPU, it is designed for general purpose serial processing, handling one complex at a time. A GPU has a massively parallel architecture. It consists of thousands of smaller, more efficient cores designed for handling multiple tasks simultaneously. While originally built for rendering 2D and 3D graphics, modern GPUs are now used for GPU, or general purpose computing and graphics processing units tasks, such as deep learning, scientific simulations, and cryptocurrency mining. This because many mathematical problems like matrix multiplication can be broken down into thousands of independent small calculations that a GPU can solve all at once. Then for the SAP1 operation, which is the simplest possible one, it's an 8-bit computer designed to introduce the basic concepts of a stored program computer. Its operations revolve around the movement of data between internal registers through a WBus. So the key components is the accumulator, the other subtractor, and the controller sequencer. Then for the SAP1 programming, the SAP1 involves using a very limited set of 5 instructions because there's no high-level language, right assembly language, or the mnemonics, which is then translated into machine code, which is the binary. So we have here the LDA or the accumulator. Then the add or the addition, the sub for the subtraction, and out for the output, and halt for or HLT for halt. So that's all for the SAP1 operations. So in this example, we will assume that the true is stored in memory address EH and the number 3 is stored in memory address FH. So how the computer executes this? So we will use the fetch cycle for every instruction above. The sub one first goes through a replaced fetch, where the address is sent to the memory, and the instruction like the 40 is pulled into the instruction register. So for the execution, once the instruction is identified, the controller sequencer sends out a specific pattern of third control bits. For that instruction, return the RAM output bit and the register in bits simultaneously, and trigger the sum out and the accumulator in bits to finish the math. So the result, the sub-one only has 16 bytes of memory, the data, the numbers to entry, must be stored at the very end of the memory space, or the CF, so they don't get confused with the instructions at the beginning. Thank you.